everyone. I'm Amit Rapaport, and I'm a security researcher at the Israeli Threat Hunting and Research Team of Windows Defender ATP. I'm a so-called Windows boy, born and raised on Windows OS and Microsoft technologies in general. And my favorite topics have always been low-level OS internals, reverse engineering, and exploitation. Today, I'm going to tell you a story of how an alert in our product has led me to the discovery of a zero-day vulnerability, one which could be exploited in order to gain full local privilege escalation on a machine. Then we're going to see a demo, hopefully a working one, so stay tuned. This is where our story begins. You're all probably familiar with this infamous creation of the WannaCry ransomware. So let's have a little reminder of WannaCry. It was a major outbreak happened during May 2017. The malware demands few $100 in exchange to the user's data decryption. It infected more than 200,000 machines in just a few days, which is huge, and it propagates mainly through an SMB-v1 kernel exploit known as Eternal Blue. Eternal Blue kernel exploit delivers a payload called Double Pulsar, which is a super lightweight kernel mode backdoor. Double Pulsar was allegedly developed by the NSA Equation Group and was leaked by the shadow brokers. Double Pulsar enables the attacker to inject code into user mode by sending a specially crafted SMB command remotely to the machine. In the WannaCry scenario, it was used to inject the main payload into the LSAS process. So, how double pulsar injection technique works in a nutshell? Let's have a look. First, it allocates a read-write-execute memory region in the address space of LSAS process. Then it simply copies a shellcode from the kernel into that newly allocated buffer. Finally, what it does is to inject a user APC into some victim thread in LSAS, targeting this shellcode hosted by the memory region. So what is an APC? APC stands for asynchronous procedure call, and it is basically a function which gets executed asynchronously by a specific thread. A user APC is a user mode function which is called by the thread when it enters, normally when it enters a special state known as alertable state. So, as defenders, how do we protect our customers and basically detect such kernel threats? Double Pulsar is a kernel mode backdoor, right? It runs in the kernel, so installing hooks on Antos kernel in order to monitor the usage of these APIs is non-sustainable, right? PatchGuard will crash the system. Drivers cannot register notify routines on either the memory management or the APC operation used by Double Pulsar. So what can we do, basically? Is it even possible to detect? Yeah, well, we recently made it possible. In the last October update, we introduced new instrumentation to Antos kernel, which provide the required optics to detect such kernel threats. Both memory management and APC operations are now performed by kernel callers are now being traced with dedicated events, which can be consumed by anti-malwares and via the threat intelligence ETW provider, which is super because that's exactly what we need for double pulsar related threats. Cool. Yeah, so one day, so we shipped the kernel sensors in the last October update, and one day I came across an interesting alert, which is our main story here today. As you can see, Windows Defender ATP alerted or observed an anomalous behavior on some machine of kernel to user code injection. So what happened on that machine? When I examined the alert artifacts, I learned that a kernel code was allocating an executable memory region in the address space of services process. Then, a kernel code injected the user APC into an arbitrary thread in services, which means that this is some sort of the kernel to user code injection, APC injection we've seen before in double pulsar. But the thing that drew my attention the most was the fact that services was the only affected process in that system. That means that it eliminates the scenario where some AV or security product injects everywhere in order to install its user mode or hooks. Someone was targeting from the kernel the services process. Could it be some kind of double pulsar variant? Let's find out. Now, next I went to hunt the source to find which kernel code actually triggered the code injection. How can we tell? Well, it's quite hard to tell, basically, and the reason is that kernel code can be executed in arbitrary context and asynchronously, and you can't know for sure what is the origin of this code execution. So I tried to look for indirect evidence which could lead me to the source somehow, and I looked at the recent events fired on that machine just before the actual alert fired. Then I found out that there were a bunch of drivers loaded just before, to the kernel, of course, just before the alert was fired. And looks like by the path of these files, it belonged to software called PC Manager of the Huawei vendor. So looks like Huawei's kernel drivers were loaded just before the alert was fired. All right. So I decided to look online for Huawei PC Manager. Who are you and what are you doing? So it turns out that this software has 3 documented key functionalities. First, it makes sure that the hardware components are working correctly and the drivers are up to date. Second, it serves as a hub for Huawei mobile devices. And third, it serves as a front end for Huawei online support. Oh, and one more thing, this software is pre-installed on any Huawei laptop, also known as MateBook. So it means that it's quite prevalent. Still, you wouldn't expect this kind of software to do anything as targeting a system process and inject code into it from the kernel, right? For what cause? So in order to make sure it doesn't, I downloaded the installer from their website. I installed it on my VM. I extracted the suspected driver and started analyzing them. My strategy was basically to dump their imports and to check whether they are actually using some incriminating APIs which could result or trigger the kind of behavior we observed in the alert. And then I found this guy, which is one of the drivers, which is using both a user memory allocation function and an APC insert function, which is quite uncommon among hardware-related drivers. So this looks suspicious. I decided at this point that I want to take a deep dive to get a better understanding on what this driver tries to do with these functions. And maybe it has something to do with the behavior we observed. So my entry point to the code was basically the area where these functions were called. So first, what the driver does is to allocate a page with read-write execute permissions in some target address space. Then it resolves the function addresses of both create process and close handle functions. Next, the driver populates the newly allocated page with basically 2 portions. The first portion is a code one. A whole function implemented in the driver was copied into that buffer. The other portion actually contains, it's some sort of a parameter block, and it contains data. First, it contains the resolved function pointers, and it also contains some sort of a string. And the last thing the driver does in this function is to actually inject a user APC into some arbitrary thread in the context of the target process. All right. One last thing I found out in this whole code flow was that it is being called by in a some process termination context, meaning that some process has to terminate so that the code injection will be triggered. All right, so what does the driver try to gain exactly? We know that it implements, it looks like the pattern we've seen before, right? It looks the same as double pulsar did, but what does it try to inject? I mean, it's supposed to do mostly hardware-related tasks, right? So in order to find out, I started reversing the function which is being called by the driver, right? The APC is injected, the driver calls the function in that newly allocated memory region. I inspected the code. And there I found a position-independent code implemented as part of the driver. And what it does is really, really simple. First, it extracts the function pointer of create process and invokes the string, which is part of the parameter block, which stands for a command line. So the whole purpose of the shellcode being run in services is to basically execute generically a command line. A generic command line executor in services. Now it's even much more suspicious. I mean, why would the driver inject a generic command line executor into services? So, I mean, what process gets created here normally? I had to find out. So what I did at this point was to attach a WinDBG kernel debugger and set a breakpoint at the location where the memory region was actually populated with the parameter block. At the parameter block, we mentioned that there is the command line string. So once we get a breakpoint hit, we can inspect the content of the parameter block. And getting the intention of the driver right, we can see which command line is passed to the shellcode and supposed to being executed. Great, so I set a breakpoint and waited and waited and waited, and nothing happened. And then I realized that the reason is that some process has to terminate so that the code injection will be triggered, right? But we don't know which process has to terminate. The best way I know to simulate such a thing is to reboot the machine. So I rebooted my VM a few times, and then I got a breakpoint hit. And I inspected the content of the parameter block and found out that the process which is supposed to be created from services is called made book service, and it is located under the PC manager directory. So it's supposed to be some sort of a service, I guess, and it is running with a /startup in its command line. So what's going on with made book service and what is it doing? Let's find out. So when made book service is running with /startup, it does a really simple thing. It actually queries for the status of some service called MBA main service. And if it is in a stopped state, it starts it via the normal service control manager API, just called start service. But, I mean, this whole thing of injecting code from the kernel into services with a generic shellcode which execute a command line just to do that, I think that's a bit of an overkill. And who is MBA main service? So in order to find out, I went to the registry and found out who is it. And I found that MBA main service is actually made book service itself. So made book service is running with a mode which revives itself. And the whole purpose, the whole goal of the injection was to revive made book service. So what are we looking at exactly? Is that some kind of a watchdog? And if that's a watchdog, then the process which gets terminated just before the code injection is triggered is actually made book service. So in order to prove that claim, I had to somehow break the code which actually triggers the coding injection, right? So what I did first was to inspect the code which decides whether or not to inject the shellcode and execute the rest of the process execution. And it turns out that the decision is based on some terminated process properties. If the terminated process name belongs to some global list residing inside the driver, then the code injection takes place. The driver actually iterates for every process which gets terminated on that global list and checks if it's there. If it's there, then it performs the code injection. So if our theory is correct and Matebook service was indeed trigger this code injection, then it has to be on that list, right? So in order to find out, I reattach the kernel debugger, set a breakpoint at the location where this global list being iterated, and inspected the list. And guess what? Matebook service was there, and it was the only entry on that list. Cool, so looks like a watchdog. Let's have a quick recap of what we saw. Matebook service, it terminates, then it is being revived by the driver. The watch process list is stored in the driver global list, and it is some sort of a variable. It's not like a fixed list of processes. So I wonder if that's a list and that's a variable, could it be extended somehow? Can someone register its own executable into this list dynamically? Well, it appears that it can be extended. And when I further analyzed the code, I found out that there is a designated IO control exactly for that purpose. And not only that, the driver doesn't validate anything about the newly registered executable, meaning that the driver can watch your executable once you're able to invoke this IO control handler and actually register the executable you want it to be watched. So all we need to do is to be able to communicate with the driver over its device object. So we need to get a valid handle to the device object, right? At this point, I had a few insights. The first one was that the device object was actually created with a DACL granting everyone read-write access to the device, which is a great news, right? Because we could just open a handle to the device and it will work. No one enforces access to the device. So I tried it and I failed. And I wondered, why did I fail? Because the security subsystem doesn't enforce access to the device. And then I realized that the driver must have been implementing logic which actually somehow rejected my request. And the location where this logic is implemented is probably in the ERPMJ create dispatch routine of the driver. So there I went there and analyzed the code, and I found out that the driver implements some sort of an authentication mechanism which actually validates the caller process by its main executable path. It must belong to some sort of a whitelist, trusted executables which permitted to communicate with the driver. All right. But if the executable is trusted, it doesn't mean that the whole process is trusted, right? No one guarantees that the whole process is not already compromised somehow. The main executable could be some of the permitted one, like Matebook service, but if we somehow infect the process itself, we can just freely communicate with the device, and it would work, right? Not only that, but if we infect our own Matebook service by injecting code into it, by the way, we can do it also from a low privilege process. Why? Because a parent process has full permissions over its children, and it can inject code into it, even if it runs with low privilege. Which means that from low privilege, we can register any executable we want to the watchdog. If we can register any executable we want to the watchdog and it's being watched, does that mean that we can abuse this mechanism to gain local privilege escalation? Yes, we can. And how do we do it? We actually create and inject our own malicious code into some, let's say, matebook service, which is a trusted process. And we do it from a standard user context. Then we craft a special I/O control from that context to register our own controlled executable, let's call it LPE POC. Then what we do is we run LPE POC and exit immediately. Why? So that the watchdog will revive it as a child of services, hence inheriting services primary token with local system permissions. And that is, ladies and gentlemen, the privilege escalation we found. Thank you. Now it's time for a little demo. Yeah, so this is my machine, and I'm logging in with a weak user. Of course, that it won't work at the demo. Yep. And now, let me show you that this CMD is indeed running with as a weak user. And wait. Yep. So it's running as a weak user. It doesn't possess any administrative privileges, and it does not belong to any administrative group. Not only that, I ran this CMD with low integrity level. So from that context, we're gonna elevate privilege into local system. And how do we do it? I'm moving to the POC directory, and what I'm doing is I'm running my own implementation of process following. Actually, I borrowed it from a guy named Idan from GitHub, so thank you, Idan. And what we're going to do right now is to use process following injection technique to hollow the main executable from the matebook service process with our own controlled LPE POC, which actually executes the rest of the exploit. Process following was used here just as an example injection technique. It could be either injection technique you like, it would work. Now, and I'm praying and crossing my fingers, if that works, we're gonna see a new pop-up of CMD, which actually runs elevated with local system permissions. So let's pray. And we have a pop-up. Thank you. So let's get back to the presentation and do a quick wrap-up. So today I told you about the journey I had when I first encountered an unusual alert in the wild, investigated, and eventually found a vulnerability. What makes this case so exciting is the fact that I didn't go there to find vulnerabilities. I actually just followed a suspicious behavior, and there it was, right in front of me. One thing I wanted to take from my talk today is that we, as a security community, should pay more attention to OEM software, because it might be easy targets for attackers. And for the software devs out there, try not to reinvent the wheel each time. Use existing mechanisms, like in the Watchdog case. They could have just made this service unstoppable and use service error recovery to revive it each time it terminates, instead of re-implementing everything. And this way, this whole issue would have been resolved by design. So Huawei released a fix last month. So if you're still running a vulnerable version, please update your PC manager. I'd like to thank Huawei PSRT for ending this case both professionally and quickly. And I would also like to thank my manager, Itai. Thank you for being there, supporting me and encouraging me to go on. I wouldn't have done this without you. Thank you all for listening today. Bye-bye.